Hey, ladies and gentlemen, welcome to another video. So I thought it would be kind of fun for me to kind of go through this Mr. G's mistakes worksheet and kind of correct the mistakes in front of you on this video. And you can obviously compare whatever corrections you made to the corrections that I make on this video. And by the way, if you caught something that I don't catch on this video, comment on either the video or Google Classroom, because I wouldn't be surprised if I missed something. It happens. But before we get into that, I just want to say, I know how much of a bummer it is that that you don't have your spring break, the official spring break. So for this week, I'll try to kind of present some fun activities. And we have, I have an extra credit assignment on the horizon coming out. But one thing I found that helps me sort of get over the bummer of losing the break is to break into a fresh pack of Couch Potato brand snack foods. Couch Potato brand snack foods now with 4 fine fake flavors: Beyond Peanut, Beyond Coconut, Beyond Pretzel, and Beyond Umami. All right, so there you have it. Most of those don't even make any sense, but I don't know, whoever's paying these marketers did a poor job of hiring. But anyway, whatever, I just read what they want me to say. All right, so in all seriousness, though, it is a bummer that we don't have the spring break we were expecting, but let's get through it with some attempts at humor and I'll try to have some fun. So I'm going to go through and grade this paper, which, as we hopefully understand, is riddled with mistakes. So I'm selecting the red pen, and here we go. Now, I'm not sure exactly why it looks like this was written on the back of the Declaration of Independence. I don't have old-time parchment paper in my home. I have just plain white paper, but I guess when I took the photo, it had a parchment paper vibe to it for some reason. But anyway, all right, that's neither here nor there. So we're going along the premise that it is my belief that students with eyes that are not brown can do more push-ups on average than students who have brown eyes, right? And so, as you know, we did collect this data. This data is actually from my students from last year. So these are the true numbers. These are just samples, of course. But out of the students with brown eyes, there were 78 of them, and on average, they did 18.78 push-ups with a standard deviation of 12.55. And the students without brown eyes, there were only 17 of them, but on average, they did 21.47 push-ups with a standard deviation of 9.93. All that information is actually true, but of course, just because X bar 2, the sample average, is greater than X bar 1, the sample average of students with brown eyes, that doesn't necessarily mean that this is a statistically significant difference. So that's what we're going to test right now. All right, so the plan. A good start, defining the parameters. So mu1, we're going to let be true average number of push-ups by student with brown eyes, and mu2, true average number of push-ups by student without brown eyes. So that's a very good start. I want to always define my parameter to begin my plan. Now, we start running into troubles with the hypothesis. The null hypothesis says that X bar 1 minus X bar 2 is equal to 0. Well, first of all, this null hypothesis is centered around the sample, which doesn't make sense. I'm not interested in running a hypothesis about the sample. I mean, samples are variable. So maybe I might get a sample such that X bar 1 and X bar 2 are the same. I might not. It doesn't really matter. I'm not interested in comparing the samples to one another. Ultimately, that's not what I'm interested in. Ultimately, I'm interested in what are the parameters relationships with each other. So my null hypotheses should always deal with the parameters. So I'm going to change this to say that mu1 minus mu2 is equal to 0. That'll be my null hypothesis. My alternative, similarly, I don't care about the relationship between the samples. So I'm going to say that my alternative is that mu1 minus mu2. I want to make sure that this less than 0 is in the correct direction. So remember, it is my belief that students with eyes that are not brown can do more push-ups than students that have brown eyes. So students with eyes that are not brown, that's mu2. And so, yes, what I'm assuming is that mu2 is greater than mu1. Another way of saying that is that mu1 minus mu2 is less than 0. So this will be a lower tailed test. All right. State an alpha value that's completely necessary. And we should do it early on before we start crunching the numbers. So that's good. And state the procedure. But the thing is, this is not a 2 proportion z-test. Well, what type of test is it? We've obtained 2 samples and we're analyzing means. And we are analyzing means from 2 independent populations, right? So the number of push-ups done by brown-eyed students has no effect on the number of push-ups done by non-brown-eyed students. So these are 2 independent populations, and thus this is going to be what we call a 2-sample t-test. We're doing a t-test again because when we analyze means, there's that extra layer of variability within samples with respect to the standard deviation. And since the population standard deviation is unknown, that extra layer of variability is built in, and so we're going to use the t-distribution. So this is a 2-sample t-test. All right, so there we have it. That seems to be now an appropriate plan. So let's move on to the justify stage. Okay, representative sample from each population mentioned. Is that true? Let's see. Okay, he collected data from a representative sample of each population. Okay, so it is mentioned, so we're good to go. Another way of trying to justify that the first condition is to look for a random sample. So we either want a random or representative sample. In this case, representative. 78 and 17 are both less than 10% of their respective populations. Yeah, so notice that the populations deal with students with brown eyes, not just stats students, but students. So let's just take it to mean Bronx Science students, but for sure, 78 is less than 10% of students with brown eyes, and 17 is less than 10% of students without brown eyes. So we're good to go there on the 10% condition. So good job on both of those. 78 greater than 30, cool, nearly normal condition met there. 17 greater than 30, well, that's obviously not correct. And so since 17 is not less than 30, I would have to check the normal probability plot in order to see if the nearly normal condition is satisfied. However, I actually don't have all that information. So what I'm going to have to do here is for population 2, I don't have enough information to check nearly normal condition, so I will have to proceed with caution. So I'm going to say nearly normal condition cannot be verified. Proceed with caution. Okay. So it's not true that the nearly normal condition is met for both samples. It's met for the first sample, but I cannot check it for the second sample. Okay, and actually, so I see that I made a mistake in correcting my mistakes. I should say for sample 2. All right. And here we go to the show stage. So first, what I've done is, as long as the conditions are met, then I know that my sampling distribution of the difference of sample means should be distributed not normally, but using the t distribution. The center of the distribution is not negative 2.69. And I know we probably got that number because that is the observed statistic. That is the observed x bar 1 minus x bar 2. But that's not where the center of our distribution lies. The center of our distribution lies at whatever we're assuming about the parameter. That's supposed to be a 0, right? So we're assuming the difference between these two parameters is 0. And that is actually going to be the center of our distribution. The standard error, this is the correct formula. I have to just verify that that's the correct number. So I'm going to pause this for just a moment. All right, welcome back. So in plugging the numbers into my calculator into this formula, I have found out that this is actually the incorrect standard error. So the true standard error for this sampling distribution should be 2.7963. All right, so hopefully you caught that. All right, now let's get into the other information, the observed stat, x bar 1 minus x bar 2. I just want to go ahead and verify that it is negative 2.69. So I have 18.78 minus 21.47. All right, negative 2.69. So that looks good. So our observed stat is right on. Now I can calculate the test statistic by taking the observed, so this is good, observed minus expected, which again, we're expecting 0 because that's our null hypothesis, divided by standard error, which in this case we determined should be 2.7963. So that's the adjustment. And I think actually, although the denominator was wrong, when I do my negative 2.69 divided by the actual standard error, this is the true test statistic. So our test statistic number is correct. The denominator was incorrect. All right, so let's go into how to calculate the degrees of freedom. So there's a little bit of kind of a cheap way of doing it. If you go to stat, stat, scroll over to tests, and remember I'm trying to run a 2-sample t-test here. Oops, sorry, it's a little bit of a lag. All right, stat tests, 2-sample t-test. I'm going to input the stats because I don't actually have the data. So let's go ahead and input the actual statistics that we were given. So we have 18.78 for x bar 1. $12.55 for the standard deviation of the first sample. And of course, the sample size was 78. And moving on to the second sample, we have 21.47. 9.93. And going on 17. All right. Now with all that information, I of course should fill out the appropriate alternative hypothesis. Now, remember the alternative hypothesis, the way we wrote it was that mu1 minus mu2 was less than 0. That is equivalent in this case to saying that mu1 is less than mu2, which is what this symbol is sort of denoting. Scrolling down, no, we will not pool our data. We only pool with a two proportion z-test. All right, hit calculate, and this does everything for us. It also gives us the degrees of freedom that we were looking for. So in the two sample t-test, the degrees of freedom formula is just something completely crazy. And so as a little bit of kind of a cheat, we can find the degrees of freedom by running through the entire test on the calculator, just for the sake of kind of showing your work. So the degrees of freedom here, 28.365. Let's see what I had written, 28.365, good to go. So your degrees of freedom are good to go. The critical value. So my alpha level is 0.05. And remember that we're doing a lower tail test. So really the rejection region is going to be down here. So the critical value is like, where does this rejection region begin? All right, well, let's calculate that. You can either use a table or you can use your calculator if your calculator has the inverse t distribution. But what we're going to do is we're going to go to that inverse t. We're going to input two items. We want the area to the left, but since it's a lower tail test and since alpha was 0.05, the area to the left is going to be 0.05. Our degrees of freedom, which is what we just calculated, 28.365. Paste, enter, and now we are getting our critical value, negative 1.7, which was not what I had, so that was wrong. In other words, I would need to observe a difference that is negative 1.7 standard deviations below the assumed mean. And let's see if that actually ends up happening. So really, to calculate our p-value, we want the probability that, well, no. We calculate our p-value based on what we observed. And what we observed was an x bar 1 minus an x bar 2 being less than negative 2.69. So remember, this probability is based off of the hypothesized distribution, which we're looking at here, the thing that I just boxed. So assuming mu1 minus mu2 is 0, what's the probability of observing an x bar 1 minus an x bar 2 that is less than negative 2.69? An alternate way of stating that is, what's the probability of observing a test statistic that is less than negative 0.962? These are equivalent, and that p-value should be 0.1721. Let's see if that's correct. I'm going to go back to the I'm going to go to second distribution. I'm going to do TCDF. My lower bound is going to be negative something very large. My upper bound, I have to use the test statistic for TCDF, would be negative 0.962. And the degrees of freedom, again, are 28.365. enter, enter. 0.1721, 0.1721, good. All right, so a lot of mistakes here, especially with the sort of the displaying of the sampling distribution. But now everything is sorted out. Let's move forward. So we have to now make a decision, and obviously we can see that this p-value is greater than our alpha value. And if that's the case, we would actually fail to reject H null. Right, because if our p-value is in our alpha value, that just actually means that this red rejection region, let's see, is smaller than the p-value. So the area, that purple area, is greater than the red area, which means that what we observed, our observed stat, did not travel along into the rejection region. All right. So we would fail to reject H null. Let's go back to the red pen. We would fail to reject H null, and we would say that we do not have evidence to support the claim that students without brown eyes can do more push-ups on average than students with brown eyes. And this should make sense. I mean, why would it be that your eye color determines how many push-ups you can do? So this is actually a result that I expected in reality. And I'm glad to see that that's how it worked out. All right, so there you have it. Those were my mistakes. They are now corrected. If I missed something, let me know. And ladies and gentlemen, as much as, I was joking around earlier, I do think that, as long as we stick together and try to get through this time with humor and just with also some little bit of hard work, we'll make it out the other side. And otherwise, I hope all is well, and take care, ladies and gentlemen. Talk to you soon. Bye.